we're going to take a look at two optimization questions. And today we'll take a look at this one, question 9, and we'll do this one without a calculator. But it's most likely that in a test or exam that this actually ends up in the calculator section. Okay, so let's jump into it. We have here a cylinder and it says the total of the circumference of a circular end and the length of a cylinder is to be 120 centimeters. Okay, so we're taking the circumference of one of the circular ends and the length of the cylinder. So we have 2 pi r plus the y, the length of the cylinder, and that is equal to 120. Also, we know, looking at it, that we want to find the values of r and y that will maximize the capacity, meaning the volume. So we also have a situation where we're looking at the volume equals pi r squared times the length, which is y. Now, of course, because the volume function has 3 variables and we need it to have 2, that's why we're using this earlier constraint so that we can find y in terms of r or r in terms of y. But obviously this is easier to rearrange to be y equals 120 take 2 pi r. And so putting it into the volume equation now, we will have pi r squared, and instead of y, we'll put 120 take 2 pi r. And I'm going to simplify that a little bit, so I get 120 pi r squared take 2 pi squared r cubed when I expand that out. Now that I have my function ready to go, we need to start looking at actually doing the calculus on this question. Okay, so dv dr is equal to, differentiating, we'll get 240 and we get pi r take 6 pi squared r squared. We make that equal to 0, and while I do that, I'm going to factorize out 6 and also pi and also r, because that is a common factor to the whole expression. So here we've got 40, subtract, and then here we're left with pi r is equal to 0. So in the first instance, we know that 6 pi r equal to 0 leaves us with r equals 0. And so that is not a solution that we'll examine any further. On the other side, we have 40 take pi r is 0. So 40 is pi r, and r is 40 over pi. Okay, from there, what we want to do is examine and make sure that we have shown that that solution is actually going to be a maximum solution to this question. So to do that, we could use the sign test, but let's look at the second derivative test by differentiating this again. So we get 240 pi take 12 pi squared r. And substituting in our r value, we can have a look at what will happen here. So we have 240 pi take 12 and then pi squared and then 40 over pi. So we can see here that we get a situation where this pi cancels out and leaves us with pi. And 12 fours are 48, but 480, so we're left with 240 pi take 480 pi. So that leaves us with negative 240 pi. And since that's a negative, we know that from the concavity, we're looking at a maximum. So we've done all the calculus, all the justifying to show that we know that the solution that maximizes the capacity of this container is a radius of 40 on pi. So now we just need to answer the question being what is the radius and what is the length of this container. So therefore, the radius is going to be 40 on pi, and that was centimeters. And the r value, and we just need to go back and look at what was our expression for y. It was 120 take 2 pi 40 on pi. Again, the pi's cancel out here. And we just have 120 take 80, giving us 40 centimeters.